we need to refresh real quick parametric and polar graphing. We did this early on in the year when we did our pre-calculus stuff, but this is going to be coming back real quickly. One change that I'm making from the way I taught things last year is I didn't do anything with parametric and polar calculus until the very end of the year, and I think it makes more sense to learn how to take derivatives with not just rectangular functions, which are the ones that we're used to, but also parametric and polar as we go. All right, so as we go through the differentiation methods, not only are we going to talk about how to take derivatives of rectangular functions, but we're also going to see how we can take derivatives of parametric functions and polar functions, or I should say relations, not necessarily functions. So just a quick refresher. If we have something like this, okay, this is a system of parametric equations. And so what is this system of parametric equations telling us?
T cannot be negative.
Oh, t could be negative.
Just coordinate. I mean, in the y.
So if we plug in a t value, it's going to give us what?
X
An x and a y value, right? So for any t value, there is an associated point. So like, for example, when t is 0, we put 0 in for t for x and we get 0. We put 0 in for t for y and we get 1. So when t is 0, we get the point 0, 1. And we could do that for any t value. We could do that for any rational or irrational t value. So we could plug pi in there and get a value for x and y. And it turns out that because this is continuous and this is continuous, our parametric curve is going to end up being continuous also. So we could plot like discrete points, discrete being separate points. So we could put in 0 for t, 1 for t, 2 for t, 3 for t, and then we could connect the dots and have a pretty good idea of what this parametric relation would look like. You could also graph this in your calculator. You guys remember how to do that? Okay. Since both of these are continuous, like I said, then we're going to end up with a continuous parametric curve. And since both of these are smooth curves, they don't have any kind of corners or cusps or discontinuities or anything like that, then the parametric curve is also going to be continuous and a smooth curve. So what that means is we can take derivatives of that also. Okay, so even though it's a parametric curve, we can still find the slope of a tangent line to it. I don't know off the top of my head what this looks like. It's going to be, I think it's just going to be a parabola but shifted over and flipped, but you can't see the flip because it's symmetrical. What we end up with is a curve that looks like this. It doesn't really matter. It's a sideways parabola that opens to the right. And we could pick a point on that parametric relation and find the slope of the curve at that point. So we're going to be doing derivatives with parametric equations also. And they're going to be very closely related and follow the same rules that we're going to see with rectangular relations. Let's talk briefly about polar graphing. Part of our pre-calculus discussion was talking about how we convert polar equations to rectangular equations. We're just like with rectangular equations, what we're going to end up doing is we're going to try to find the derivative just like before, so we would say dy dx. We'll also look at derivatives like dr d theta, or d theta dx, or dy d theta, and we're going to talk about the change in variables with respect to other variables and what those things mean. We can kind of look at what this would look like. Anybody know what this would be? It would be a circle, yes, with a radius of 2, exactly. So the center of that would be here at 2, 0, and it would hit the y-axis at 4. And if theta goes from 0 to 2 pi, it's actually 2 revolutions of that circle. We could get the full circle just by going from 0 to pi. And so just like with parametric equations, we could take a point here and say, okay, this is when theta is 4 pi over 3, and we want to know what the slope of the tangent line is when theta is 4 pi over 3. And so we can take derivatives of this to do that. You'll notice that this equation is entirely in terms of r and theta, but in the end we're going to want dy dx, which is going to give us a rectangular slope. To do that, we're going to actually convert polar equations to parametric equations and then do our calculus on the parametric equations. Because calculus is fairly straightforward and fairly easy on parametric equations. We're also going to use those relationships that we talked about. If you remember this triangle right here, where we have a y value, an x value, and theta and r, we had x equals, you guys remember the relationship here? X equals what? R times cosine of theta. And y equals r sine of theta. And so these are going to be very valuable to us in converting a polar equation to parametric equations because, well, this itself is a parametric equation. It defines x and y in terms of other variables. And so we're going to be able to use that to do calculus. So that's coming up. We'll be doing that shortly, probably next week.